Welcome to the fourth unit of the fifth week in the Parallel Programming Concepts course in OpenHPI. After we discussed shared nothing environments, their particular interconnection topologies and the idea of doing message passing with MPI, we now want to look into more, let's say, elaborated programming models for shared nothing environments. So there are alternatives to the traditional MPI style of doing message passing applications, and we want to spend the next unit with checking whether they have interesting concepts that may help us with our parallelization problems. We want to start here with the channel approach. So programming with channels is one general idea in shared nothing environments, and we start with the investigation of where this concept comes from. And channels is an idea that comes originally from a formalism that is called Communicating Sequential Processes, CSP. CSP is a formal process algebra that was invented by Sir Tony Hoare at the University of Oxford. Tony Hoare is, for example, also the inventor of quicksort and the Hoare logic. And he defined an algebra where we treat computer systems as something that acts and interacts with the environment. And inside the computer system, we have something that is called a process. So you see the term process is reused each and everywhere. In CSP, a process is something that performs some kind of activity and interacts with other processes in the system or with the environment. This is a purely abstract definition of how a computer system could work or is working. The overall topic is well described in the Communicating Sequential Processes book by Tony Hoare. It's freely available on the internet and it's really worth a look. And in CSP we have one single concept, which is the channel concept. And this is something that is meanwhile used in a lot of programming languages for shared nothing environments. It is also available as a library for standard programming languages such as Java, because it has some interesting conditions that are very helpful in writing parallel shared nothing applications. And we will now have a very short glimpse into the algebra in order to understand where this advantage comes from. So in CSP, a process is really the idea of having an abstraction of behavior. A process is something that performs activities and it has a notion of atomic events. An event is something that comes from either other processes or from the environment to the process, and then depending on this incoming event, the process will change its behavior, for example, by sending events to other processes. So you restrict the overall idea of a running program, of a running system, to processes and events being exchanged. One very simple example from the CSP book is the idea of an ATM and a user. So you have an ATM and the user, both are processes in CSP thinking, and you have maybe two interesting events. A card event, which expresses the insertion of a card into the ATM, and the money event, which expresses the extraction of money from the ATM by the user. So you see here that by using the idea of events we express interesting things that happen. So the point of event is that whatever could potentially come from the outside and go out from a process is formulated as an event. So if you do a whole process specification and a whole specification of all possible events, you have an overall description of the system behavior. So you have all the information that is needed in order to describe the system and to understand what could go wrong inside this thing. An alphabet is the set of relevant events for an object description, so you restrict yourself to the kind of events that are truly relevant inside of your system. When you take now this idea of processes and events, you can start to define a special class of event, which is communication. So we treat the exchange of messages, the exchange of information, as just another event that may happen. A communication event is then expressed or can be summarized as something that is called a channel. A channel is an unidirectional connection between two processes. So process A may communicate with process B, and this means it triggers particular events for process B. And if you want to group these events, you can summarize them as a particular channel. Channels in CSP have, for some reasons, a so-called rendezvous behavior. So sender and receiver block until the operation is completely performed. You put the message into the channel, it goes over the channel, and then the receiver gets the message and continues. If you have such a situation that you have only one-way connections and you have blocking on both sides, rendezvous behavior, then a couple of interesting results come out of this. This is well described in the description of the formalism. For example, if you have two concurrent processes and they communicate with each other only over such a channel, they have no other way to talk to each other, then they cannot deadlock. The reason that they cannot deadlock is that there is no circular wait, so there is no channel that goes back. And if no channel goes back, you cannot run into this mutual locking scenario that we saw several times now that is typical for a deadlock situation. So if you fulfill this condition, then it is provable that a deadlock will never occur. The interesting question is now, can you write an application that fulfills this condition? But in general, this kind of thinking, this kind of idea in the channel concept makes it easier to reason about potential race conditions inside your parallel shared nothing application. So the deal here is that any possible system should be or can be modeled through event chains. So you can define your processes, you can define the alphabet of these processes, and you can think about possible chains of events that may happen. One event coming after the other. You don't know exactly what the ordering will be because you have no influence on the timing. But if you take all these possible so-called traces, then you can do some reasoning and figure out if this particular task graph and this particular communication scheme inside your parallel application may lead to race conditions or not. This is an interesting idea from a research point of view, from a formal point of view. There are some tools available. We link on the reading page. And CSP was the base for a programming language called Occam. So Occam was the attempt to take the CSP idea and map it directly to a parallel programming language. It was very famous for so-called transputer systems. This is hardware no longer being built. Occam also is no longer actively developed or used. There's some research, especially at Welsh University, about implementing the channel concept and the overall idea for other environments. For example, for Java or based on MPI or for other programming languages. So if you're interested in using something that is a little bit more abstract than MPI messaging, channels may be an interesting concept. So you can check for your favorite programming language if a channel implementation, CSP channel implementation is available. Here's one example for Scala. We saw Scala as a shared memory programming approach already in week number 3. And in Scala, you also have a channel concept explicitly in the class library available. So one example here shows you how you can do channel sharing by shared variables. If you have a shared memory system, then your channel variable is globally available in different activities, which are called actors, explained in the upcoming unit. And in these different activities, we then can use output and input operations in order to either send values or receive values from the channel. Since channels are a first-class primitive in Scala, you could also do something that is described in the right example here, where you can send channels, or more exactly channel identifiers, to somebody else over a channel. So you can take this channel, tell the other, here is another channel, please use this for your result. And this leads to the fact that even though you have only one directional channels, the target node or the target instance can answer you by using the provided answer channel. Another example is the programming language Go, which is not really designed for true parallelism, but mainly for large concurrency issues. And Go programming language also has a channel concept. This is one of the fundamental issues in there, that you have a program here. The entry point is again main. And in this program, you create a channel as a resource. And then you start a concurrent activity. This is expressed here by the keyword Go. Go say hello, start the say hello routine as a concurrent action. And then inside this method, we see a particular channel operation where the string hello word is put into the channel while the main function continues and reads a value from the channel. So again, here we have the idea that a CSP-like channel unidirectional, run the Ruby behavior, is used as a synchronization or communication primitive in our code, and we have no explicit message sending or passing here. We just use the notion of this channel. We don't care about buffering. We don't care about which kind of send or receive call we use. We just use the language primitive for channels in order to express our demand to do a synchronization between concurrent or maybe even parallel activities. When we take Go as example and continue with this, you have also something that is called select. This is something you may know from pure socket programming, and select also works in the channel world. So you can take such a statement to say, I want to continue in my instance here depending on input data that is available either from one or the other channel. So by this you are able to do complex control flows inside a shared nothing concurrent application. And this basically works very good if you have channels as a first-class citizen in your language. If this is the case, then there's a good chance that your parallel or concurrent application gets a more deterministic behavior and you have better ways of avoiding race conditions. The CSP channel model is not the only channel model that is available. There were subsequent developments that tried to consider more properties of the execution environment. One example is again by Ian Foster, the task channel model. And you see that this is very similar to what we have seen in CSP. Foster defines parallel computation as something that consists of one or multiple tasks, and the tasks are executed concurrently, hopefully even in parallel. The number of tasks may vary, which is a difference to CSP, where the number of tasks is fixed. And we have input and output ports as an interface to the environment. So Foster further introduces the concept of these ports beside the channel idea, where he says, okay, we have the tasks and they can read and write local memory. They send messages to their output ports and they receive messages on their input ports. With such a model, you can then start to pair tasks by connecting the input and output ports of the different tasks. Channels therefore can be created and deleted. And they can only also be referenced. So the point here in comparison to CSP is that you again make channels an explicit construct, but you lose a little bit, you relax a little bit the hard interwiring condition. So you say channels may be attached or detached from particular ports. The interesting question is if all the promises that you get from the CSP formalism, like proof of deadlock freedom, if they still can be fulfilled by this model. Even if this is not the case, the task channel model still allows you to have some abstract thinking about your algorithm. So with such a model as CSP or the task channel model, you're enabled to develop your parallel shared nothing application without writing actual code. You can talk about tasks and channels and ports and design your parallelization strategy in an abstract way, for example, on a piece of paper, without even starting with programming. And if you have done all the race condition analysis right, if you are really sure that you have a good load balancing, if all of these things are clarified, then you can take your designed abstract application or abstract parallel application and move it to a particular programming language. For example, Scala or MPI-based C or whatever you prefer most. So this is really an advantage that you get with the channel concept, that there is an abstract thinking about your shared nothing parallelism, and then you move it to the implementation of this abstract concept for your environment. So programming with channels has advantages. Here as a summary. First, if your parallel program relies only on channels, then performance optimization works without destroying program semantics. For example, you could decide to put multiple tasks of your parallel application on the same node and use a channel implementation that relies on shared memory. So instead of intermixing global variables, OpenMP style programming with something like MPI, you could always use channels in all of your code parts and then simply twist the channel implementation with respect to the fact wherever you're on a single node with your multiple tasks, or if they really are distributed and you need some kind of network communication. The task mapping, the mapping of instances of your parallel programming to the execution environment, does not influence these semantics if you use channels, because you clearly say, I want to have a channel between rank A and B or instance A and B. So you basically only talk about the communication behavior of your code, but you're not restricting yourself or binding yourself to a particular style of execution environment. The implementation of your channel library has to deal with the fact that there may be multiple hops between your channel source and your channel destination, but this is then hidden in the channel implementation. And working with channels inside your application also allows you to build modular applications, because you can simply use, for example, something like an outport concept and implement it in your application. And this allows you to attach other kinds of modules easily by, again, relying on the channel concept.